Fleming's left-hand rule is useful in finding the direction of force on a moving charge in a magnetic field or on a current carrying conductor in a magnetic field. Current carrying conductor also has moving charges, isn't it? Hold your left hand like this with thumb at right angles to the rest of the fingers. Then fold your fingers such that the middle finger is at right angles to the rest of the palm. The other two fingers are closed, they don't really matter. So this way, you should be comfortable doing this. This is a left hand rule. Be aware of that. Sometimes you just put up your right hand because you're so used to using your right hand for most of the tasks. Most of us are right-handers, so that happens. Believe me, I have seen it happen. Let's apply this in one case. Say a charged particle is moving southward and magnetic field is eastward. In terms of the space you're in, imagine you're facing north. That's I am to your north. Your right will be east and up and down are no problem. So the direction you're facing is north. Behind you is south, right is east and left is west. Now, charged particle is moving southwards. I'm pointing this finger. This is the central finger. Well, it's middle finger, let's call it central finger so that we can associate that C in central finger with current, direction of motion of positive charge. Forefinger is the direction of the field, which is to the east in this case. Thumb points the direction of the force, so force is upward in this case. That's it, as simple as that. So how do we do this? First, point one finger in the direction of the moving charge, this moving positive charge. I'm pointing. Then rotate the other finger so that you get the right direction for the magnetic field. I got the direction for the magnetic field correctly. Thumb gives the direction of the force. If for some reason it's inconvenient to point the middle finger in the direction of the motion of the positive charge, you can point it in the opposite way. And whatever force direction you get, you must reverse it. Or you could reverse both directions and then you'd get the correct direction to the thumb. That is, you point both fingers the wrong way. Alternately, you could use the plane of the paper as a reference. For example, in the case we just mentioned, charged particle was moving southward and magnetic field was eastward. So, paper plane is, say, consider the paper plane as a horizontal plane containing, east and south, horizontal plane. So this would be north and this would be east. Now you could have, the velocity vector is towards east and magnetic field is towards velocity vector is towards south, magnetic field is towards east. So you could say this is like negative y direction, minus j bar. This is the east direction, that's like plus I bar. Since you know f bar is q into v bar cross b bar, get the direction of v bar cross b bar. So if q is positive, the direction of v bar cross b bar gives us the direction of f bar. If q is negative, you can reverse that. So in this case, v bar was minus j bar, right? It was in the southward direction, and b bar was eastward. So do minus j bar cross I bar. You will get what you want. That will be k bar, which will be upward. So that's one way of dealing with it. Well, you can also use the paper plane as a vertical plane in case you need to. So in which case up and down are pretty clear. So this will be up and this will be east. That is, you are basically showing a vertical plane containing east-west. Well, again, this is like j bar and this like I bar. And if you do I bar cross j bar, you will get the direction of k bar, which will be out of the plane. So out of the plane of the page. So you know how the directions are in terms of the paper. Also realize, well, if you're given V bar and B bar, you can find F bar. But if you're given force and velocity, that is, if you're given the velocity, force and the velocity, you can only find the B perpendicular component. B parallel does not affect the charged particle, so if there is a B parallel, you would never know it. So Fleming's left-hand rule can give you only the perpendicular component of the magnetic field if you know V and F. So the perpendicular component is uniquely determined. What do you mean by that? Now the perpendicular to V can be anything in the, this is southward, right? Anything in the vertical plane containing east-west, any direction in that plane. But then that direction is uniquely determined. That is, B perpendicular is uniquely determined. B parallel, well, could be this way or the other way. So Fleming's left-hand rule, if V and B are given, no problem, we can get F bar. But if we given F and V, you can get only B perpendicular. B parallel you can never find. Also, if V and B do not have a right angle, you cannot use the Fleming's left-hand rule as it is. You can split B into components. Supposing B were, say, this way, southeast. Split that into components. Well, the component southward and component, well, eastward. So don't bother about the parallel component to V. Consider, then use the Fleming's left-hand rule. Or do again V bar cross B bar. Right? Use the right-hand rule. V is this way, right? V is towards southeast, so I am pointing V, swing V towards B. It's pointing upwards. This is right-hand rule. We're curling V towards B and we're getting thumb as the direction of the force. So this is it. Either you could use the plane of the paper, in which case, well, here we had charged particle moving, well, which way? Southward. So this way, V was like this. Take this as the reference, V bar. This is V bar, and the magnetic field was this way. So you can swing V towards B using right-hand rule. Swing V towards B using right-hand rule. That will give us the direction of, or this is like minus J bar and this like I bar. So find the direction of minus J bar cross I bar, which is, well, whatever direction you get. Isn't it? So you will get minus J bar cross I bar is plus K bar. K bar will be out of the plane. That is upward in this case. That's it. Well, learn to use Fleming's left-hand rule and be comfortable with holding your fingers. Practice it a couple of times maybe. And then again, I told you this. First point one finger, the central finger, the direction of central, we call it central finger, the middle finger, in the direction of motion of the positive charge or the direction of current. Okay, if it is a current carrying conductor, this will point in the direction of the current. Then rotate the other finger so that you get the magnetic field correctly. As simple as that. Don't mess up, don't be clumsy with this. Okay, first one finger in the right direction, then rotate the others.